is go live or
Yeah.
leave, then it's saying here go and leave.
Mm-hmm.
And now you are leave. Done.
Okay.
Now at the end of the day, you have to press end stream here, this red button. Okay.
Okay. Okay, I see.
But simply you can don't touch it at all.
Yeah.
You can just stop share. That's it.
I understand.
The only wrong point, well, not wrong point, but strange point about today's seminar is that apparently, which we underestimated maybe, it's Easter this Sunday. Many people go, let's say like this.
Yeah, I see.
On the other hand, let's say Indian, Chinese, Korean, Japanese people don't go. Russians as well. It's not Orthodox Easter, no. So let's imagine that we will have some, let's say, average or something like this presence, okay? But this we cannot change, okay?
Anyway, well, it already happened, so we cannot change it.
Ah, yeah. At least we have speaker here. It's already something. Hello.
Hello.
Hi.
Hi, Sumati.
Hi. I would like to say that I don't forget about sending.
Hello.
Yeah, very good, very good.
I will do it.
So,
Hi. Thanks for this invitation.
Hi, nice to see you.
I'm going to just take a short, I'm just going to get some water and come back.
Okay, good.
Madam Stravan, may I ask you, do you also hear a little bit distorted voice of Sumati,
Yes.
or it's only to me?
Yes.
Okay, so you and me, so it means its connection on Indian side is not that great.
Yeah.
Okay.
Hello, Irina.
Hello.
Hello. Yeah, so next week we will have Capazzello and we will have 1 hour earlier.
Mm-hmm.
Okay.
So in Moscow at 5.
Yes.
Okay.
And you still didn't send title of your talk.
Yes. I said.
But at least I hope you're okay with the time. Because,
okay, it seems to me it's okay. Yes.
No, it's
Also,
okay.
Professor Starovinsky didn't send the title, so.
And also Professor Dvalli.
Okay.
But yeah, we'll see. And also Modesto.
Okay.
Yeah, because today we're supposed to submit our paper to archive, but maybe we will not ready. So in any case, it will be the title of this paper, my talk.
No, I mean, the most important was actually not even the title. Title is okay, but the timing, because some people complain about timing. Some people want earlier, some people want later, some people simply don't reply at all already for months. So it's kind of...
So what is the typical audience that you have?
Sorry?
What is the typical size of the audience that you have for these talks?
Well, this depends. It
Depends on the
changes.
speaker, I'm sure, yes.
It changes from, I don't know, from 30 to 300. So it depends very much.
Depends.
No, that's a huge 300. So you have a good, very stable Zoom license then for this.
Yeah, well, usually people from US and Canada, for them it is very early. So that's why we allow the talks in YouTube so people follow from YouTube. But on an average, we do get like 40 to 50. But sometimes it goes to 100, more than 100.
No, sometimes it really goes.
Yeah.
I mean, 300 is a lot to
Yeah.
on Zoom. Yeah, that's a lot. So should I try to share my screen?
Yeah.
Yes, yes,
Oh, yes,
yes.
please, it would be nice.
So I'm going to use my iPad so that I can
Yeah.
mark things on it. You know, yeah.
Yeah.
Вы
Is that
знаете, не получилось. Сейчас, подождите, я выключу в Zoom этот самый звук.
Also, there is a tradition that all people come every, let's say, last minute, or maybe 2 minutes after, like bad students. But it's okay.
Yeah.
Also, well, we forgot about Easter tomorrow. So,
No, it's not like we forgot about
yeah.
it. It's like, for some people it's Easter, for some people it's not Easter. We advertised it all over the world, I'm
Yeah.
now in China. In China, it was holiday yesterday, okay, for example.
So,
And
so you're in which university are you in?
I'm in China, in Shanghai Tech University. They just started a theoretical group, and we are, well, I'm now actually the only theoretical person here. One more will come in September.
Oh, lovely.
Also expect 2 postdocs to come in September with me. I already, selected them. And there are students here, so it's supposed to be rapidly growing group. Because
very nice. That's great.
University forked quite an amount of money.
Sorry?
The university gave a lot of money to build theoretical group, especially.
Okay, very good. That's great. That is a positive move in general.
No, generically here it looks like they have general wish to invest a lot of money in science. Actually, one postdoc, he will be from India. Actually, I suggested some other, some lady also from India to come, but she finally said that in favor of parents, she's going to stay in India.
Okay, so I see. Do you know the student's name, the postdoc? Can you remember the postdoc's name? Where he might be from? No, okay.
Well, in this case,
I have actually also encouraged my students to look also at places in China because it looks like there are opportunities, and so it's good.
Well, in this case, I suggested to Abhishek Naskar from Mumbai to come. But another person, well, I technically, I don't remember now exactly the name, but I can find, I think it's an extremely bright girl. It's an extremely bright lady. She impressed me really, and I was very happy to give her offer, but finally she said she's going to.
That's really pity, yeah. In fact, I think one person who's in quantum gravity, Gaurav Narayan, I think his name is.
Yeah. He's in China, right? Yeah. I met him actually. I was in China.
Okay.
Yeah.
So he has moved to Bangalore. He's got into he's a faculty he worked in asymptotic safety, right?
Yeah.
At commutative geometry. He's now faculty at IISc.
Okay. That's great to know. Yeah.
I'm going to bring my this.
Sorry, Sravan, whom you are talking about?
Gaurav Narayan.
Narayan. Yes.
Yeah, he wrote papers about this loop corrections in matter loop corrections in gravity. So quite nice papers.
Yeah. No, I know whom you're talking about. Yes. No.
So he's come recently to my city, so to neighboring institute, and so so we're looking forward to actually. I haven't interacted with him yet, but yeah.
Yeah, I met him when I was postdoc in China for some period. Yeah.
Okay.
I was in Japan actually, so a month ago. So I recently moved to UK. Yeah.
Okay.
Yes, and now actually I found this other lady to whom I was suggesting an offer is Kayal Singh. She impressed me. Well, she generically impressed me how free she discusses string theory stuff and fluxes and compactification. And also I was really impressed that she got a recommendation letter from Ashok Sen.
Okay. That's of course
I discussed with her. I was indeed impressed, but finally she said like she's better to stay in India. Otherwise, I would have here 2 Indian postdocs.
Yeah.
But it's okay.
I think like people coming to India, people are also very nervous, postdocs coming to India because it's a new place. But I think Shanghai, from all that I've seen, is a very modern city, very easy to live in and not comparable. Yeah.
I was there only one night, but even I felt very nice in that city.
It's modern, yeah. It's very also quite expensive, I can say, but well, now I appreciate very much the part of the offer which says that apartment is given by the university.
Okay.
This part of the offer is now I appreciate very much because I save nearly, I don't know how much, like about 1,000 on a rent. Rent is comparable to London here.
Oh my goodness! Oh
yeah, it's absolutely. Even only you go somewhere to outskirt of the city, then it comes to I don't know $800 at the best. But normally it goes to be like 1,000, 1,500, something like this. It's expensive place. It's quite expensive.
Interesting, yeah.
But also it's very nice because there is this traditional Shanghai universities and there is Fudan University. Now they're growing very rapidly. This Shanghai Tech University, only in Shanghai there are 3 universities.
So Fudan, there are some people also, right? I mean, I forget the names, but Cosimo, I think.
Yeah, Cosimo, Bambi, Antonino Marziano, they're there. Yes, I know these guys. At least with Antonino and with Ravan and also with Anna, my collaborator, we now organize an online conference, which will happen in 2 weeks, actually. Or even less, in 10 days. Yes, there should be some interaction here on all of this. There is also a nice ICTP IP center in Hangzhou, not far from Shanghai. They do a lot in ADS CFT, string theory and stuff around. So
this is ICTP, is it?
Well, it's named ICTP AP, ICTP for Asia Pacific. They have some nodes.
I didn't know this.
They have one node in Beijing and they have node in Hangzhou. So it's like 200 kilometers from Shanghai. So these are also good places with let's say string-oriented people or holography or also cosmology. Anna, my collaborator, is now getting position in Hangzhou, for example. So she's also moving to China, and so in principle.
What is the support for things like mathematics, more mathematical physics? Is there support for that as well?
Your question is quite difficult because, well, first of all, I'm only 2 months in China. Okay, it's hard to say.
All right.
But the most important, no, you see, but the most important, what I understood, it's very, very, very place dependent. It is very inhomogeneous, extremely. And you can find the difference few times in matter of, for example, support. For the same category of employment, for everything, salary, for additional benefits, and for additional grant. For example, in Shanghai Tech, I supposed to get roughly, it's a school algebra. I have to be able to divide I should get, roughly speaking, $130,000 per year as external fund for everything like hiring postdocs, travels, or whatever. And I didn't hear about any other university which gives the same. But it's not like only for me. For any new faculty, they suggest this particular budget. They suggest 1 million yuan per year, at least for first 6 years.
Wow, that's impressive.
Which is a lot of money, actually. So this and this very much dependent on a place.
Okay.
So
Dear
should
friends, I think it is time to start. Sorry to interrupt your very interesting discussion. Today we have a pleasure to have a talk by Professor Sumati Surya. She will tell us about recent results in causal set theory. Sumati, please, 1 hour.
Yes, thank you so much for this invitation. It's a pleasure to be here and to talk about causal sets. So I was told that I should give a very broad overview of the subject because it's not familiar to a lot of people, which is what I will do. So I will in fact begin by motivating the idea of the causal structure post set in the continuum, and what's a very important theorem in Lorentzian geometry called the Hawking-King-McCarthy-Malaman theorem. And then I will show how this motivates very naturally the causal set approach to quantum gravity, what I call the CST paradigm, causal set theory paradigm. And one very important part of this paradigm is the continuum approximation. How do we look at this discrete substructure and say that this has any continuum-like properties in it? And this is this whole idea of geometric reconstruction from these post sets, getting geometry from order theoretical ideas. Because of this audience, I thought I'd also focus a little bit on how you do quantum fields on causal sets, in particular, some recent work on entanglement entropy calculations and the interesting things that it tells you. If I have time, and I do not promise that I will reach all of this, I will tell you about some very recent results with Steve Carlip on how a certain entropic problem in the path integral, in the Lorentzian path integral of causal sets we have a solution to that particular problem. So let me begin with the very beginning, which is with the causal structure post set. And the idea is that if you have any spacetime, give me any spacetime which is causal, which means that I have no closed causal curves, not time-like, no null or mixed. Then associated with this is a partially ordered set, because between any two elements or events in the spacetime, I can basically assign an ordering if they are ordered by causality. And if they're not, then they're not. They're space-like related to each other, and that's why it's a partial ordered set. And the property of it is that it's acyclic. So that means that if X precedes Y, it can't precede itself. And this, of course, is a little subtle because you could end up using an irreflexive condition, but let's just stick with this particular notation here. And it's also transitive, which basically tells you that light cones are nested one inside the other. So if X precedes Y, Y precedes Z, then X precedes Z. So this is just basically what a partially ordered set is. Now, if I look at any Lorentzian spacetime, which has this causality property, then I know that at every point I have light cones, which one is future light cone, one is a past light cone. And this is what allows me to extract this partial ordered set. And it's actually absent in any other signature, because once I have another time direction, then time is connected. The time directions are connected, which means that there's no distinguishing a direction. There's no time direction. There's no causal direction. So, of course, this is very essential. This is sort of a feature of this particular signature spacetime. It's absent in Riemannian geometry, but it's also absent in other signature spacetimes. It's very special to Lorentzian spacetime. Under conformal transformations, we know that this causal structure, light cones go to light cones, so there's no change in the causal structure, so the post set remains the same. And the idea that this causal structure, it's absent in Riemannian geometry, it's absent in these other things. It's got some special essence of Lorentzian geometry, and people have been thinking about it for a long time, really ever since special relativity, with Rob's understanding of the theory of space-time from the perspective of relations, of space-time relations. And going on to Zeeman in 1964, who showed that the group of chronological automorphisms, that means, you take Minkowski spacetime, map it into itself via an automorphism which preserves the chronology relation, which means the time-like relation, then this group is in fact, is the group that is an automorphism group that does this is isomorphic to the group of conformal transformations of Minkowski spacetime. Okay, so that's a very interesting result. Very soon after, Kranheimer and Penrose tried to axiomatize causal structure in this very important paper, which is still used today by Lorentzian geometers all over. And the idea is to extract from a spacetime its causal essence. And so I've just sort of extracted this little piece here, which you can read, which basically is, in some sense, a harbinger of the causal set approach. So the idea is there. So all of this, there was a lot of trying to understand what causal structure does. And finally, this very important set of papers, one by Hawking, King, McCarthy, and later followed up by Malamud, is basically summarized in the following way. But before I say anything about it, let me quickly define a causal bijection, which is that if I have two spacetimes, M1, G1, and M2, G2, I extract their chronology coset. So in other words, I'm not talking about causality, I'm talking about time-like relations. Then I have a causal bijection if things are related in one spacetime and they're also related in the other spacetime and vice versa, okay? So X precedes Y in spacetime 1, and f of X precedes f of Y in spacetime 2, and vice versa. That's a chronological bijection. A causal bijection, sorry, this should be chronological. Causal bijection is one that does that for causality. A conformal isometry this is what I mean, just that it's related by a conformal transformation. So the theorem says that if you have two spacetimes and they're related by a chronological bijection, then they are conformally related. In other words, that causal structure coset that you extract from one is the same as the causal structure coset you extract from the other one. And that gives you everything about the spacetime up to the conformal factor, okay? We did some work to show that this chronological bijection also implies that the dimension of the spacetimes are the same. So here's where the causal set hypothesis takes off. You say, well, okay, here's this beautiful result in Lorentzian geometry. It tells you that maybe we shouldn't be thinking about spacetime simply as a pseudo-Riemannian geometry, but rather something really intrinsically different. It has this intrinsically different structure, which is a causal structure coset. And let's start with that coset and say, can we think of that, a quantum theory based on that, a quantum theory of gravity based on that? And that's basically ideas that, have been around, but were finally crystallized first by Mirheim in 1978 in a lost CERN preprint, not lost, but unpublished CERN preprint, and finally by Bombelli, Lee-Meyer, and Sorkin. And this is what we will call causal set theory. And the idea is that you take any continuum spacetime, because you can think of it as a causal structure coset plus the local volume element, which is the conformal factor, that you can now think of the following. You can say, well, let's look at that local conformal factor and a local volume factor and say, instead of thinking of it as a continuum, if we say that for every space-time region, and this is very essential, it's a space-time region, like the space-time region between this event and this event. That's an Alexandrov interval, and that contains only a finite number of fundamental space-time atoms. So it's a finite, locally finite causal coset. So this condition of local finiteness, that every finite volume region must contain a finite number of fundamental space-time events is this hypothesis of atomicity of space-time. So basically, a causal set is a locally finite post set. And the idea is that the causal set, by doing this discretization, you not only have the causal structure post set, but you also have the volume element by counting. Just by counting the number of elements in this volume here, you get out its volume. But of course, you only recover the continuum as an approximation. So order plus number gives you space-time. So here's the hypothesis that essentially, instead of talking about space-times and quantizing space-times, we think of a quantum theory of causal sets. So first quantization is that you've discretized, but the full quantum theory is of one of causal sets. And so they can be of all kinds. So any post set is a causal set, which is locally finite. But then very importantly, and this is what distinguishes it from some of the other theories which use the same term causal sets, is that the continuum approximation is very important. So we have used the continuum approximation to motivate our theory, to say Lorentzian geometry tells you this about space-time. And that's our motivation. So we would like to stick with that motivation, said for those causal sets that are approximated by continuum space-times, because not all of them will be. The space of causal sets is much bigger than the space of continuum space-times in this approximate sense. But in order to do the correspondence, I want to maintain this order to number relation. Of course, I want to make sure that the ordering in the causal set corresponds to the causal ordering in the space-time, but I also want to make sure that the local counting that I do corresponds to the volume in the continuum. And for this, yeah, sure.
You prefer asking questions in the middle of the talk or at the end?
You can go ahead and ask. I'm fine. And if I don't finish my talk, that's also okay.
Okay.
Yeah.
Thank you. What do you exactly mean by space-time atom? I mean, how do you define it?
Right. So we want to say that what we imagine to be space-time, right? I mean, the best example is if you think of the air around you, it looks to a classical person very continuum-like stuff, right? I can describe it in terms of velocity fields and so on and so forth. But if I really look down close, it's made up of these atoms. And so the idea is that really the objects that we're looking at are discrete, fundamentally discrete, and that's it. I'm not, and that they're fundamentally discrete, but they're ordered by causality, okay?
Okay.
And really speaking more generally, the ordering, if I look at space causal sets of this kind, some of which have nothing to do with space-time, as I will explain in a few minutes, even then this order relation is what I'd like to call a proto-causality, because it's not yet causal, because I'm not talking about the continuum. It's something that is a fundamental order relation. And that's what order and number are the basic key ingredients that go in.
Okay. And the short question is that you have the discrete space-time. How is it different from LQG?
Oh, it's completely different. So LQG starts off with a Hamiltonian formulation. In the continuum, you have tetrads and so on and so forth, which are defined, in the connection, these gauge connections and so on. But you start off with a continuum space-time. And then, of course, you do get a discrete, the spectrum for your operator. But here we're kinematically itself making a choice of what our degrees of freedom are. So continuum is an effective, it's like, at some level, it's like string theory where you say the fundamental degrees of freedom are strings. The continuum is an emergent property. That's exactly the same idea. In that sense, it's similar.
Okay.
So how do you make this continuum approximation? And so here I've said we do it through a random lattice. And let me just say a few more words about that. So the idea is that if you want to have a number to volume correspondence like this, you also want it to be diffeomorphism invariant. I mean, you don't want it to matter which coordinates in which you're doing this, because ultimately you want to get out a space-time. You don't want to get out a set of coordinates. You want to get out a space-time. without a preferred set of coordinates. So here's an example of using a regular lattice in Minkowski spacetime. And if you try to do, say, okay, let me look at this region here, and that volume there has so many elements in it, right? In a regular light cone lattice in 2D. Of course, if I do a boost, that same region is going to be completely empty. There's nothing here. So under such a transformation, and more generally under a coordinate transformation, a discrete lattice, a regular lattice, will basically not allow you to make a number to volume correspondence. And it's not very dissimilar to what you would do in a spatial context, where you say, well, you know, if I want approximately so many points in some region, the best way to do it is through a Poisson process, right? One way, possibly the best way, and that's an open question, but that's what we do. We say we're going to look at a Poisson sprinkling into the spacetime, extract a causal set, and that is our discretization. How do we extract the causal set? We do the Poisson sprinkling where, you know, this basically V is the space-time volume. We do it at a given density rho. And this tells you that on average, the number of points in any space-time region, space-time causal diamond, is given by the volume up times the density of sprinkling. So this correspondence works in the mean. It's an average correspondence. And of course, it has fluctuations. The question is whether it's optimal or not. But the other thing is that, so apart from this Poisson sprinkling, then you add in relations coming from the spacetime. This is just the continuum approximation. This is how we make a connection between causal sets and the continuum. And then, therefore, you have this idea of a faithful embedding at some density, where you basically say, if I have a spacetime, then what are the causal set? What can I say about a causal set that I would extract from that? Or vice versa, if you show me a causal set, can I say that this is actually approximated by a particular spacetime? Really, what you get is an ensemble of causal sets kinematically through this random lattice. It's really a random lattice, if you like. An important feature of this Poisson process is that there's a statistical independence of the process in disjoint regions. Okay, so this helps you do calculations. What is also very important is Lorentz invariance, local Lorentz invariance, and this is a very beautiful theorem due to Bombelli, Henson, and Sorkin. As I said, and so one thing to remember that if you had a regular lattice, say in a Riemannian lattice, a regular lattice, you know very clearly that you're going to lose the symmetries of the space-time, right? Of the space. Just in 2D plane, if you did a regular lattice, a square lattice, you lose the symmetries of this plane. But if you did a random sprinkling by a Poisson process, you know that there's no obvious preferred directions in this. This theorem basically says the same, or says something very similar, in a very careful mathematical language. But it also tells you something special about the Lorentzian case. And it tells you that even in one given realization, you cannot make a choice of direction in a way that is equivariant, which is invariant under Lorentz transformations, because if you did that, you would end up with a measure on this hyperboloid of future directions, which you have in Minkowski spacetime, which is infinite, which a probability measure which is infinite, or zero. So this is the theorem that allows you to show that in the causal set, even though you have a discretization of space-time, because of the randomness, because of the Poisson randomness, you strictly have Lorentz invariance, and that in the sense that there are no preferred directions. But what you do is you give up something quite dear to us when we do continuum physics, which is locality. There's a very fundamental sense of non-locality in causal sets, which is also what makes its phenomenology very rich. I will not talk about that much today at all. And so what do I mean by non-locality? So if I take a finite region of space-time, for example, and I look at the nearest neighbor, so I have a point here, and I look at its nearest neighbors. By that, I mean that if I have 2 points here, and I have a relation between them, there's no intervening point like this between them, okay? So that's a nearest neighbor. I can't get closer than that. So this nearest neighbor, if I think of a graph, that's called the valency of a graph. But if I put this in Minkowski spacetime, then I realize that because of the fact that the probability for a link is related to the invariant volume. So let me here actually draw this, sorry, and I apologize for my bad drawing. But I have a hyperboloid, for example, and in any point here, the volume, so this gets narrower and narrower, right? It sort of asymptotes to the light cone. And this space-time volume becomes thinner and thinner in this frame. So you can go all the way up the light cone. So the number of nearest neighbors reaches all the way up the light cone. And this is the kind of non-locality we have to deal with. So we have discreteness, Lorentz invariance, but what we have to give up is locality because it's not a graph of finite valency. And this in particular makes it very hard to construct or reconstruct tangent spaces. One has to do something far more complex to, okay, in particular, you asked me about loop quantum gravity, which uses a Hamiltonian formulation, right? Where you take a Hamiltonian formulation of general relativity. You have a, you start off with spatial hypersurfaces. Here you can ask, well, what is a spatial hypersurface? I mean, it's, in some sense, it's very easy because it's a set of points that are not related to each other. And if you want to think of one that's Cauchy, you might say it's a set of points that are maximally unrelated to each other, meaning you can't add on any more points in here. But so you can say, well, you really have something like a Cauchy hypersurface, but not quite, because a Cauchy hypersurface is one that is a summary of its past. If you give initial data, then everything is determined from then on, right? I mean, you don't have any more freedom in a globally hyperbolic spacetime. But here, even in a causal set that you've extracted from a globally hyperbolic spacetime, you have the possibility of what I will call these missing links, okay? So if this set here is my set of space-like related points, okay? Let me draw that a bit more carefully. This red set here is a set of space-like related points. And I say, oh, aha, I found myself a Cauchy hypersurface. But there are relations between points here in the past and the future, which do not even transmit through this. So it's more like not a Cauchy surface, it's more like a Cauchy sieve. It has holes in it, okay? And that means that you cannot construct an initial value problem in this. And this is another reason why it becomes a lot more complicated when we're dealing with causal sets. So the other thing about non-locality is that because things are related with respect to, the Poisson distribution happens with respect to the space-time volume, okay? Imagine something that the distribution is uniform with respect to the space-time volume. But that means that sets of measure zero will not happen. Which means that even to recover null geodesics in such a situation is very complicated. You have bulk properties, but boundary properties are much harder. Okay, so just to say it and summarize it. So this non-locality in summary makes it very non-trivial to obtain discrete analogs of continuum geometry, but somehow we managed to do it still. And an important conjecture, which we call the fundamental conjecture of the theory, is that if you have a causal set, which you say is actually corresponds to a continuum spacetime, it cannot correspond to another continuum spacetime unless the two spacetime are related to each other, close to each other, up to discreteness scale. In other words, if give me a spacetime and I have a very tiny region in which I replace it with, say, a lot of complex topological information, like a lot of wormholes or something, in some very small region, which is much smaller than the scale of discreteness, then the causal set obviously cannot distinguish between these two. And we would turn that on its head and say that those are physically not relevant. That amount of detail in the continuum is not relevant to the discrete substructure. So we're never interested in the continuum limit. Never say never, but I mean, we do use a continuum limit to help us, gauge how well we're doing. But fundamentally, from a fundamental perspective, discreteness is fundamental. We don't look at the continuum limit. And that distinguishes this approach from many of the other approaches. Of course, one can say, well, what does it mean for two spacetimes, Lorentzian spacetimes, to be close? And this is something that was very exciting for me to go to this conference in Vienna and the Erwin Schrödinger Institute, where there are a bunch of mathematicians really interested in this question. When are two Lorentzian geometries close? And they're trying to attack this question from multiple directions and are also interested in this way, interested in causal sets, because they sort of exemplify the idea of a Lorentzian geometry, of a discrete Lorentzian geometry. So this is just to say that there's a lot of work in that area. But the thing that we want to do is to do a geometric reconstruction. So give me an ensemble of spacetime that causal sets that you've obtained. And from that, just by counting, looking at structure in the causal set, can I extract interesting information about the spacetime? This is one aspect of causal set theory, which we call kinematics, geometric reconstruction, where we're not talking about the dynamics. If I have time, I'll touch a little bit upon dynamics towards the end, some interesting new results we have. And so the idea is that any order invariant you have, something that doesn't care how you've labeled the causal set, is an observable. So labeling is like diffeomorphism, okay? In this, so if I've labeled the points, nothing that I extract should depend on that labeling. So for example, here, if I say, well, I'm going to count the number of links here. Sorry, I should use this. I'm going to count the number of nearest neighbors. I say 1, 2, 3, 4, 5. Then it doesn't matter how I relabel this. I still have 5 nearest neighbors. That's it. And that's an order invariant of this coset. And likewise, I can distinguish and so on. And these are different orderings. This is different relabelings of it, etc. But now I can say, well, if I'm able to tell you what that order invariant means geometrically, then I've done some bit of the job that I wanted to do, which is to say that, oh, then those two manifolds that I want to be close have to have the same geometric properties, because this causal set that I've obtained encodes that geometric property, okay? So this is a very important part of what we do. So let's go into examples, because that's always useful. The first example is that of space-time dimension. So give me a space-time, and I will extract from that an ensemble of causal sets, okay? And remember that that ensemble, the way I generate it is through a Poisson distribution, which is through uniform sampling of the space-time, and that's really key. Now that you've uniformly sampled the space-time and you've got out your ensemble of causal sets, you can begin to construct order invariants and ask, well, what does these correspond to? So if I consider Minkowski spacetime, and in particular a diamond, causal diamond, that is an Alexandrov interval in Minkowski spacetime, then I can calculate the expectation value of the number of relations in that spacetime, in that region. And I do it just by using the Poisson distribution. I just use the fact that, okay, if I have this causal diamond, how many elements are there, pairs of elements are there that are related? All I need to do is the first integral has to do with just the fact that it lies in this region here. The second integral has to do with the fact that the second element lies in the future, lies in the future of the first element. The second element lies in this region. So that's what this here does for you. It restricts the region. So just by doing that calculation, I find the number of relations. And what is interesting is that when I look at the average number of relations, that I find that the constant here that I get, so of course it's related to n squared, the mean of n squared, but it also has something that the dimension of the space-time comes out. And so I can invert this to obtain the space-time dimension using what's called the ordering fraction, because I just have to then look at the number of relations and divide over by the total number of possible relations, which is n choose 2 on n elements. And that gives me the ordering relation, and that's just a function of the dimension. So if I were to invert that, then in Minkowski's, for an ensemble that I extracted out of Minkowski's spacetime, I get 2 dimensions. And so this can be checked in multiple ways, in particular through simulation, that this is exactly what happens. But this is what we do. This is the name of the game. We basically look at the uniform distribution and we try to extract geometric information from it. You can do the same when you look at a Riemann normal neighborhood, which has curvature in it, and you can get out not as simple a formula, but you can get out a formula for space-time dimension. And there are other dimension estimators, but another one which is very interesting from a Lorentzian perspective. For those of you who love your special relativity, you will remember that the time-like path, the geodesic, that is a maximizing geodesic. It's not a minimizing geodesic like it is in Riemannian space. It maximizes the length. That maximizing of length, which is this extremization, but in particular maximization, is something we can actually implement on the causal set. And this was done actually by using results of Bolobash and Brightwell, combinatoris, in really way back, to show that if you just count the number of the max, so if you have 2 points here, x and x prime, and you basically looked at the longest chain that you can construct between them, the longest one, that's like the longest path that you can construct, then that is proportional to the time-like distance, okay? So here we have a situation where we have the discreteness, but through counting, we're able to extract information about the space-time. This is one in many. I'll just quickly go through this. We can construct topological invariants of the spatial hypersurface. And we rethink even the continuum think of the continuum in terms of the Hawking-King, McCarthy-Malaman theorem, which is causal structure plus volume element. If you can parse it like that, then you can always do the same thing in the causal set. And that's what we do. We construct the spatial topology and this was work we did several years ago, I guess, almost 2 decades ago. But I thought, this is an important part. So we construct the anti-chain. We then find a way to topologize that anti-chain, because otherwise there are no relations on it. This is a spatial set of points that are spatially related. We topologize it, we cover it in a specific way, and you extract out what's called the nerve simplicial homology from this. And you can show very clearly that under the right circumstances, in the sense of, given the right amount of density of sprinkling and so on, you recover the topology or the homology of the spatial hypersurface. This also leads us to a definition of spatial distance function, which we've been working on for some years now. And in particular, it gives you some very nice way of thinking of induced space-time, spatial distance on the hypersurface, using just, light cone volumes. So this is a way of thinking about not only the discrete case, but also continuum from this purely Lorentzian perspective. Very important in this was the construction of the discrete Einstein-Hilbert or Berenka-Sadowker actions, which is basically the question that in, say, in dynamical triangulations, we have the action is given by the Reggie action, right? I mean, by looking at edges and looking at the simplices and how they attach to each other. The Reggie action gives you the discrete Einstein-Hilbert action. So the question is, what was it for causal sets? And using a very ingenious method, which starts off by looking at the D'Alembert operator for a scalar field and putting this in a Riemann normal neighborhood, it was found that the action is really given in a very simple way. I mean, the coefficients are non-trivial. So if you just focused on the four-dimensional case, then n is the number of elements in the causal set. N0 is the number of nearest neighborhoods. Okay, just count the number of nearest neighbors, like this. Then you count the number of next to nearest neighbors. Then you count the ones that are next to nearest neighbors, which can come in two flavors, and so on and so forth, and you put them together to construct the discrete Einstein-Hilbert action. And this was a very important step. We can also show that in flat spacetime, when you take this, there are some hidden boundary terms, and in flat spacetime on an Alexandrov interval, this gives you, in fact, this action gives you the boundary contribution from the joint term, which is also very interesting. We can also construct the spatial Gibbon-Hawking-York term in the action. I won't say very much more about that. Very recently, like I said, we can't even construct null GD6 in the space, but then through, inspired by this work of Penrose and Fronheimer, in 2 dimensions, we came up with a proposal using what are called horizon molecules, which were studied by Barton, Council, Dowker, Gould, and Jubb, to obtain the area of a horizon. But those horizons were defined with respect to the continuum. So the question is, just from the purely discrete structure, can you define horizons? And at least in 2 dimensions, we think we have a proposal for doing this, which I've just sort of very briefly shown here. So in the interest of time, I'm just going to move ahead, but if there are any questions on this, please do ask me. I think I've rushed through a lot, but there is a lot to rush through, so.
Okay. Thank you very much for your very nice talk. Questions, please.
Yeah, so I was just going to stop very briefly now and continue. Sorry, Irina. I haven't quite finished my talk. I have a lot more, but I will.
Oh, I see. I
see.
This is just some small stop before.
Yes, just in case there are questions.
Okay.
I have a few more things to talk about, but which I think might be interesting to people. So.
Mm-hmm. In any case,
I have a short question.
Yeah.
How do you describe a time evolution of geometry? What kind of equations governs that? Because
right. So this is to do with dynamics. So far, all I've been talking about is just kinematics, meaning there's no dynamics involved. I'm not telling you how these things appear. And that is the full quantum dynamics of causal sets. And I will only get to that towards the end, because that is a difficult question. We have some new results on that. We would use a path integral to define that. But right now, we're just saying, well, first, get me the right geometric invariance, purely order theoretically. And that's already a huge exercise, a non-trivial exercise. Now that we have the action, we can actually go and do dynamics with it. But what you've generated, what the whole causal set represents is space-time. So you really want to sum over space-times to get sum over histories, path integral, path sum. That's what you want to be able to do. Okay. So, yeah, okay.
I have a question.
But you have to, yeah, sure.
Yeah, I didn't understand exactly how you managed to reconstruct or at least extract the dimension of spacetime starting from the Poisson sampling. because at least my naive intuition would be that to do the sampling, you must suppose that you already know the dimension of the set you are sampling.
Right. So here it's like a blind test, right? So you do the sampling and you give me the causal sets. Okay, and I'm going to now, I don't know where you got them from, but I'm going to run this test on them and I'll tell you what the dimension is. So of course it looks like, but you're using the continuum all the time, etc. But now if you had a dynamics and these things actually arose from the dynamics, and we have many examples of dynamics. We have done a lot of work on Monte Carlo simulations of path sum models. And there you can get out ensembles of causal sets. And you can say, what is the dimension of the object that I'm getting? And ask whether it looks like the continuum or if it's fractional. So the first part is just to be able to say, right? To be able to identify. And I think this program is often not there in many approaches because one just assumes that you take the limit, right? But we don't want to take the limit. We want to say it's something intrinsic to this structure. Yeah. I hope that's clear.
Thank you. It's very clear now.
Yeah. Okay. Thank you. So let me just say a few words about QFT on causal sets, because I think with this audience, it might be more interesting. Which is that one of the questions one might want to ask is, well, let's just, even though there are no tangent spaces, I can ask, well, let me try to define a quantum field theory for a scalar field. That's the simplest thing I can do, and I can define scalar fields on this object in a causal set. And the idea is to basically, and this was the idea of Johnson, I'm just going to summarize what's on my slides in the interest of time. But this is the idea of Johnston, who was a student at Imperial, which is that there was given this PhD problem to solve, and it turned out to be actually very, very profound, his solution to it. And he started off trying to do quantization of a quantum field on a causal set. He started off first by constructing green functions on causal sets. But then he said, how can I quantize it? And I don't have the tools of quantization. I don't have Hamiltonian tools of quantization on the causal set. What can I use on this structure? And he thought a lot about what you do in the continuum. And for a free scalar field, which is Gaussian and so on, if you look at the 2-point function, that really represents for you the vacuum. That's the vacuum. That's equivalent to the vacuum for a free scalar field. But you can, from the green function, for the advanced and retarded green function, construct the Pauli-Jordan operator here, or the Pauli-Jordan function here. And that's, of course, the Peierls bracket. This is the Peierls bracket, which tells you the space-time commutation relation for the field. And if you think of it as an integral operator, so when I say an integral operator, I've got a finite space-time region, and I've got an integral operator on that, where I'm talking about things which are L2, these functions are L2. Then this integral operator is Hermitian and skew symmetric, the Pauli-Jordan operator, which is really the commutator, the Peierls bracket commutator. And the eigenvalues of this come in pairs. You can use these eigenvalues to define your vacuum. Instead of thinking of coordinate systems and modes and so on and so forth, you use this eigenvalue of this operator, this integral operator, to define the vacuum, because the vacuum is then just the positive part of this operator. This has led to very interesting studies even in AQF, algebraic quantum field theory by Fusterberg, Broom-Fredenhagen, trying to understand this. There are issues in the continuum, but we're not going to be concerned with that, because the key takeaway is that if you know the Pauli-Jordan operator, and that can be defined purely in terms of causality, you can quantize the system. And this is really the profound takeaway from this. And on a causal set, you can define very simply green functions. Let's just take the very simplest case of 2D. In 2D, we know that the massless green function for a scalar field just has support only in the fast light cone, the retarded green function. And so that's just basically telling you what are the elements that are related, right? So that's just pure causality, nothing more. And the causal structure coset, or the causal set, has all that information. I think there's a weird lag in what I'm saying, but it's okay. I think it's all right. And so using that, you can construct the green function. You can also generate the massive green function, comparing it with a continuum. They're basically things that are constructed in the following way. If you have a chain like this, you add no weights to the ends, but to any link, you add a weight of half, and to any relation, you add a weight of half, and to any stop in between, you add this weight. So in other words, you can generate just from the causal set, from these relations, you can generate this green function, where this is just the set of k element chains. Okay, that is so many elements between them, k elements between the related elements in between. Okay, so this is a bit hard to say slowly because I'm running out of time, but importantly, it generalizes to certain curved spacetime cases. And using this, we can employ Sorkin's spacetime entanglement entropy calculation. Again, this one uses the spacetime form of, because again, we had the 2-point function, we have the Pauli-Jordan operator, all of these are spacetime quantities. And we can use these to define, and that's what Sorkin's entropy calculation does, is to calculate entropy using just these quantities, okay? And solving this mixed eigenvalue equation. And in several examples, we can show that this entropy gives you back the standard continuum entropy. But that was all in the continuum. Now, when you apply it to causal sets, you can see immediately that this can be applied because, like I said, you can define a green function and therefore you can quantize a field. And so you can ask the question, say, in a causal diamond like this, if the red larger causal diamond, you have the smaller black causal diamond, you can say, well, what is the entanglement entropy of the field restricted to A with respect to this field in the full larger diamond? And this was what Sorkin and Yazdi did, both in the continuum as well as in the causal set. And what they found was very surprising. They found that even though the causal set has a fundamental UV cutoff, this cutoff is a very strange cutoff because of non-locality. And without doing anything, you get out a volume law. You don't get an area law. But if you did truncate it, so the spectrum of the SJ operator has this particular character, and if you did truncate it, you would get out the right law. You'd get out the quote-unquote continuum law, but the full discrete theory has a volume law. We have repeated this in the diverse situations, in particular in de Sitter spacetime, and we found pretty much the same answer. And really the question, which we don't yet have an answer to, which I think is a very promising direction, and there are these very interesting papers in the literature on entanglement entropy that talk about the role of non-locality on area theorems. And I think it suggests that maybe what we think of as an area theorem is only relevant at a certain scale. At least that's what it seems from a causal set perspective, that fundamentally what it is a volume law, but that you have to go to very high energies to really probe the volume. These are speculative ideas, but these are essentially what causal set theory seems to throw up. Finally, in the few minutes left, I will talk about causal set dynamics. As you asked, how do causal sets grow? So there's multiple ways in which we can approach this, partly because we have, we need to explore all avenues. The first is to simply construct a partition function, right? You just say, here's my causal set, here's my space of causal sets, so the sample space of all causal sets. And here with this little n, I say I'm restricting to the space of n element causal sets, and then I will take n to infinity, okay? I will take n larger and larger, and I'll look at the asymptotic limit. So I construct my partition function like this with the standard way that I would in gravity, but now it's discretized. Another way to do it is to look at these so-called state sum models, where I do an analytic continuation, but I don't have time to play with. I can't Euclideanize because a causal set is fundamentally Lorentzian in character. So I have to introduce an analytic continuation parameter beta. And now I can analyze this on the computer and look at what happens. And one of the things features here is a ubiquitous phase transition, which is a first order phase transition that we find. There are also these sequential growth models, which are sort of very much, bottom up, basically a very fundamental approach to dynamics, which says, we don't know anything about the Einstein-Hilbert action. We just have some intrinsic dynamics of causal sets, and we try to generate this. So the classical models are well understood, fairly well understood, I should say, but the quantum models were just taking the baby steps in this direction. So today, in the last few minutes, I will focus on this, some recent results on the Lorentzian path sum. This is basically, like I said, a sum over all possible causal sets. You're taking all n element causal sets. So here's a great exercise, is try to construct the set of all 3 element causal sets, 4 element causal sets. The space grows very rapidly. In fact, it grows super exponentially. It grows like 2 to the n squared upon 4 plus 3n upon 2 to leading order. And this was something that people who were interested in posets from a combinatoric point of view had already found in the 70s. Kleitman and Rothschild showed that this is how the space of causal sets grows super exponentially, but also that typical causal sets have this particular feature, which we've started to call the Kleitman-Rothschild posets. They have 3 moments of time. Even if n grows, they just get fatter and fatter and fatter, okay? As n becomes larger and larger, they just get fatter and fatter. It's not like they add in more layers, there's not more time. And already you can see, and there's a very clear way to test whether these objects are like space-time, because we've already done our work. We know how to recognize causal sets that look like space-time. And when you look at this, in multiple respects, it fails to look like space-time. Okay, so what about these? These are actually as dominant to leading order as the space of causal sets. So they really swamp out everything. So the space of causal sets is completely dominated by the K-Arco sets. Suppose by a miracle you remove them, then you still have a hierarchy of subdominant posets, which is something that was found again by person Deepak Dhar, who won the Boltzmann Prize, but is a statistical physicist, but did this work very long ago during his PhD. And the point is that they're subdominant, but they're still really, really dominant. So the question is, what are we summing over? Why are we summing over these objects that look nothing like space-time? If you step back a bit, then one justification is that even in the path integral, in the continuum, the majority of paths that you have are just continuous. Okay? They're highly jagged, they're very non-classical, they're not smooth paths at all. They don't look like a classical path. So the question, of course, we want to ask is, well, I mean, does this action win over the entropy that's coming from this? This is the entropy coming from this. Does this action win over that entropy or not? And do manifold-like causal sets stand a chance? Just to remind you of the action, you have to sum over nearest neighbors next to nearest neighbors, next to nearest neighbors like these, which come in either flavor, and so on and so forth. And there's some finite number of these that you have to sum over. Okay. And so you have to be able to count the number of links. You have to be able to count the number of all of these n element intervals to calculate the action. So this is just a summary of our recent results. We started off by this work by Loomis and Carlip, where they said, okay, we can't deal with a more complicated case. Let's just bite off something simpler, which is just the next to leading order contribution, which is from 2 layer posets. And there they showed that since here it's easy to calculate the action because it's only the links, there's nothing above. So you can only have nearest neighbors contributing to the action. So that simplifies things a lot. When you do that through a very nice saddle point calculation and through some actually very nice approximations or bounds that they put to leading order, they found that there is a suppression in this of these posets in the partition function, and in any dimension, and in any dimension of the Einstein-Hilbert action. And what we showed later was if you use the same, only the simplified action, which is just counting links, you can show this for all the layered posets. They're all suppressed. What we did much more recently, which is still one paper still in preparation, which is work with Peter Carlip, Steve Carlip, is that all the results that we've shown so far actually show that even for the Einstein-Hilbert action, the action wins over this crazy degree of entropy. This is somewhat of a big deal in causal set theory because so far there was a sense that we're biting off too much, that these really bad posets will contribute and swamp out any meaningful contribution from manifold-like causal sets. Just to give you a final perspective on this, if you think about what is it that causal sets is doing, we really are looking at, even if we're looking at manifold-like posets, we're looking at all possible dimensions. And we want our action or to be able to pick out the right dimension. In string theory, you pick out the right dimension because you require that through a RG flow, the critical points of the RG flow pick out for you the critical dimensions. Here, we don't have the same thing. We are not and we can't again put in dimension by hand. We want dimension to come out of the theory. The only thing we can put in by hand is the action. And so while we have some rudimentary ideas how to do this for manifold-like causal sets, this is still an open question. So let me summarize very quickly. I think in summary that causal sets is now quite a mature field of quantum gravity research. And causality and discreteness are sort of the cornerstones of the approach. Some recent arguments by Faye Dowker and Jeremy Butterfield suggest that if you have causality and discreteness, then this is at least to the scale that you're interested in. This is causal set theory must be at least at that scale, the theory of quantum gravity. A very important prediction from this theory is that of the smallness of the cosmological constant, which comes about as a fluctuation in a sort of unimodular approach to this problem. It was predicted by Sorkin in 1987 in an unpublished work, unfortunately, but it's still there in a conference proceeding. So here are just some open questions, and let me stop here. Thank you so much for your attention.
Okay, now this is really the end. Thank you very much once again for your very interesting talk, a very nice presentation. Okay, questions, please. Please raise your hand. I see one question by, I don't see who asked this question.
I think they've said all my best wishes for your, okay, so somebody sent me a private link, so I will write to them directly.
Mm-hmm.
Yeah.
Okay. I see a question from Giuseppe. Giuseppe, please ask your question.
Yeah, thank you. And thank you for the very nice talk. Very interesting. A question that comes to my mind is what happens if you apply all of this formalism to the black hole information paradox? Since maybe with the discreteness of space-time, you could somehow count the states for the black hole entropy.
Yeah, so I mean, we don't have an answer to it in quite a complete sense. There are hints of things that we think are consistent with what we have. So I'll try to say very roughly what I think. So in particular, I mean, so in terms of the question of unitarity, okay, it is very linked to the notion of spatial hypersurfaces and a state which is evolving in time. In the perspective that we have, we would imagine that, for example, behind the horizon of a black hole, many things could happen. Just to give you an example, in the sequential growth models, we have this idea that you can have a break, which means that's a point. It's the equivalent of a Big Bang, okay, or a post where the universe collapses into itself, and then so on and so forth. But what happens at that point is simply that you have a single element. So there's nothing singular that happens. For a black hole horizon, of course, you have the singularity, but if that singularity corresponds to some highly quantum regime in which something else is happening, there's a further growth of something else, then it's, from a GR perspective, a completely fine thing for a quantum universe to grow in behind the black hole. So I think that to imagine that the one asymptotic region should have all the information, depending on how you define that information, even if it's not unitary in that, it may very well be well-defined and probability conserving in the right way in the full theory. So that's sort of the perspective that we have in general about this problem. Having said that, there is no, unless we can construct a fundamental quantum dynamics that does this for you, right? Where you can actually see. So if I can show that in my partition function and solve the full partition function and find that the kind of, here's an example, in this particular regime of the theory, I get spacetimes in which I have something that looks like Schwarzschild, but I have some quantum structure that is there and that's growing into a new universe, then that would be it. But we don't have that. We don't know as much about. So that's my very rough and sort of ready response, but I'm happy to have a conversation with you about it later. Yeah.
Thank you very much.
Okay, I see one more question from Hong Wu. Please ask your question.
Yeah. I have a question. What how to use set theory in ADSFT and
yeah, you're asking me about causal set theory and ADS-CFT. Yeah. Okay, good question. So one of the things that is very important is that you have, you see, we need to have, for every finite space-time volume, we need to have a finite number of causal set elements. You imagine in ADS space-time, if you're beyond the point of, you have a point and it's geodesic, it focuses to another point, right? P and Q are conjugate to each other. Q is to the future of P. This is what ADS space-time looks like. So we can talk about causal sets as long as they're on ADS spacetime, as long as they're within that region, because once they go out of it, then you have then you basically will have an infinite volume, but you would like to have a locally finite coset, right? Because it goes all the way to the boundary. So let's stick with that. Let's just say that we have a region of ADS in which we're within the point, the points where P and Q focus, right? And so all volumes are still finite and so on. Because of the fact that, so it's a very strange thing. So we've not calculated the kinds of things that people calculate in ADS. But if you sprinkle into the space-time, one of the features of ADS is that much of the volume is really stuck to the boundary, right?
Boundary.
I mean, the space-time volume is kind of accumulates towards the boundary, because obviously you go out to infinity, right? The space-time infinity, scribe plus and minus are one object, which is a time-like boundary, but that's infinity. So most of the volume is sort of focused out, it's outside. When you do this, you find, and because of the fact that you have a negative cosmological constant and so on, you find that if you've sprinkled into ADS region, most of the sprinkle points actually lie on the boundary. This is something that Raphael and Nospivo, was then a student of his, tried to simulate. But of course, in ADS safety, you want to make correlation between bulk and boundary. It's not entirely clear to us how to do this in causal sets, but possibly there's something to do there. I'm not sure. But thank you for that question.
Okay.
Okay. More questions, please.
I have a nice
Okay, good.
In the context of cosmology. Well, I'm like usually. Well, I'm sorry. I'm bringing again LQG point of view. In LQG, there is a concept of discrete space-time. Somehow, they propose a correction to the Friedman equation, and there is a cosmological bounds happening there. Do you have such a thing in causal set theory?
Yes, for sure. So in fact, that's actually very interesting, because in LQC, that discreteness scale, which of course in the full theory you expect that's just a regulator and so on, but when you put that in, it actually changes the nature of the theory. So I find that very interesting, because that's very reminiscent of. But in causal sets, so if I can, I'll try to draw here. So the idea of sequential growth is the following, that you grow the causal set element by element. So you start off with a single, so let me say you start off with a single element, and then you add elements to its future, or you add elements that are unrelated. So you can grow a causal set starting from nothing into something. Now, here, the kind of cosmologies, and of course we can even talk about it without sequential growth, but the kind of cosmologies that would correspond to bouncing cosmologies are things of this sort. So you have something here, some causal set here, some post-set here, and between these two eras, right, between different ages of the universe, there's a single element, and that single element is to the future of everything to its past, and to the past of everything here. And there's, it sort of divides space-time into, and in a completely covariant way. So this is a perfectly reasonable causal set to have. And in the classical sequential growth dynamics, this kind of thing has been argued to show how it can lead to renormalization of coupling constants through the bounces. Okay. So there's some very nice work that's been done to show how cosmological renormalization can take place, which, by the way, can also happen in the context of black holes with these in this way. So, yeah, so yes, we are interested in such cosmologies, but we don't yet have a theory that, from first principles is going to predict such a thing. So we don't know how exactly to construct those theories. We have toy models in which we've worked, toy dynamics, quantum dynamics, and we've shown that you can construct covariant quantum dynamics for these, but to actually answer a question like this would be something we'd like to do, but we haven't yet been able to. Thanks.
Okay, thank you.
Okay. More questions? Maybe I will ask some more general questions.
Yes.
What do you think about non-commutative generalization of all stuff that you spoke about? Do you have some ideas, or some people worked about this? In non-commutative geometry, can we introduce the notion of causality and so on? What do you think about this?
I mean, at some broad sense, I think the question is, it's an open question. Post-sets are related in a very nice way to, post-sets themselves are related in a very nice way to non-commutative geometry, but not space-time post-sets in quite this way. But there has been work, of course, in, if you think about quantum fields on causal sets, interacting quantum field theory, there's been some very nice work by people like Kasia Reiner and others. Kasia Reiner and others from York, where they basically use non-commutative algebras for the field to define, so, the star product and so on, to define interacting fields. And that can be put on causal sets. But, if there was a way, and this is very speculative, but if there was a way to, say, operatize the theory in some way, right? You place at every node, you place an operator, and you can then talk about those operators and their commuting properties or not. That's like a space-time commutation, a fundamental space-time operator that you have. These are things that I wouldn't offhand dismiss. I would say that that's definitely something that might lead to interesting structure, but nobody has done it so far. So it would be interesting to try to see whether there were non-commutative things. So Lorentzian non-commutative things, that's the key part, because a lot of non-commutative geometry is done within the Riemannian context. So to generalize it to a Lorentzian context, make it possible to then put it here.
Okay, thank you. Thank you very much for your explanation.
Thank you.
So since I do not see more questions, let's thank the speaker again. Thank you very much for your very nice, interesting presentation of so abstract and not so simple materials. So thank you very much, and don't forget to send us your transparencies. Okay?
I will do so. Yes. Thank you so much for having me here. Thank you.
Okay,
Thank you
very much
for the very nice talk.
Okay, thank you. Bye.
Bye. Bye-bye.
Sumati, you can send me the slides. I will forward them to Alexei. Yeah.
Sure, that'll be great. Thank you.
Yeah.
I'll do that. Yeah.
Okay. Thank you again. See you. Bye.
See you.